soon we're going to be going over Gauss's law, which is the first sort of one of Maxwell's equations, and it's where we start talking about the consequences of field lines, etc. So it's important that we get a grounding on what field lines actually are. So this short section just describes that. It's quite easy to get it, but it's important to understand it, yeah, because this will be what we'll be using all the way through from now on, is this concept of field lines, okay? So I'm just going to read my notes. Field lines are useful as an aid to visualizing electric and also magnetic fields. A field line is an imaginary line drawn through a region of space so that every point it is tangent to the direction of the electric field vector at that point. This idea is shown above. We will soon show, when we go over Gauss's law, that at every point the number of lines per unit cross-sectional area perpendicular to the electric field is proportional to the magnitude of E at that point. The concept of field lines was introduced by Michael Faraday in the 1800s. He called them lines of force, but the term field lines is today more consistent terminology. So what we're saying is this vector, at this point we're showing that the direction of the field is in this direction, okay? At this point is in that direction. Their spacing gives a general indication of the magnitude of E at each point. Where the lines are bunched closely together, the electric field is strong. Where they are further apart, the electric field is weaker. These diagrams show some of the field lines in two planes. So we've got these two planes here, two planes containing a single positive charge, this one here, B, two equal charges, one positive and one negative, and C, two equal positive charges. The direction of the resultant field at every point in each diagram is along the tangent to the field line passing through the point. So if we pick any point here in any of these diagrams, if we pick a point here, then the electric field will be a tangent, and these arrows here will show the direction of where the field is. Arrowheads on the field lines indicate the direction in which the tangent is to be drawn. Every field line in an electrostatic field is a continuous line terminated by a positive charge at one end and a negative charge at the other. So when we talk about field lines, we always think of them leaving positive charges and terminating on negative charges. And in the last few examples, we've assumed that. So that's always what the convention is, always to assume that electric field comes out from positive charges and terminates at negative charges. So we stick to that convention. Every field line in an electrostatic field is a continuous line terminated by a positive charge at one end and a negative charge at the other. But when depicting situations of, say, a single charge, we only show field lines coming out. So here we're only showing field lines coming out. The assumption being they will end up at an opposite charge outside the field of view. If a field line were drawn through every point of an electric field, all the space and the entire surface of any diagram will be filled with lines, and we would see nothing but a solid block of lines, So when we're depicting this, we can't draw all the field lines in, otherwise the whole surface would be completely saturated with lines. Wouldn't be able to see anything what was going on. By limiting the number of field lines, we can use them to indicate the magnitude of a field as well as its direction. In a region where field magnitude is large, such as that between the positive and negative charges here, so you can see this region is very large, the field lines are closely spaced, yeah, so you'll see the drawing here, these are all closely spaced. It shows that you've got a stronger field there. In a region where field magnitude is small, such as that between the two positive charges here, the lines are widely separated in a uniform field. The lines are wildly separated. So here you can see they're against each other, so you've got a larger separation here. So that's what that means. Lastly, in a uniform field, the field lines are straight, parallel and uniformly spaced. So when we talk about a uniform field, we're talking about this, okay? And often a lot of the problems that are solved involve uniform fields, because obviously it's easier to calculate a uniform field than it is something complex like that. In the next lectures we'll start onto this properly when we start going into Gauss's law. So we've covered kind of electrostatics, the introduction here now. Now we're going to go into Gauss's law, which Gauss's law basically is another way to find the field. we've already covered the electric field, basically the force per unit charge at a distance. Now we're going to use Gauss's law, and it's an easier way sometimes for certain problems than using some of the complex maths we've just done here. We use Gauss's law. It sort of like can completely avoid having to do lots of difficult maths. So bizarrely, although Gauss's law will be something that's unfamiliar to you when you see it, it's actually, once you start using it, the formula, you'll find that you can solve these problems, some of these last few problems, much easier. Yeah, so that's what we'll be doing next. Yeah.